Lambda days. It's great to be back here and presenting to all of you. Thank you for the great introduction, Jan. For clarity, my current job title is Head of Software Engineering for Cardano Core at Input Output Global. And the work I'm going to be presenting is work that I've done with colleagues from a company called PNSol, who are experts in system design and performance engineering, and also with colleagues from the University Catholique in Louvain in Belgium. So I claim no credit for the work, I'm just presenting it to you. So what I'm going to do in the talk, first of all, I'm going to introduce the ΔQ design methodology. Secondly, give you a case study in diagnosis using the approach. This is an iPhone launch in the UK. Thirdly, talk about a problem that's very dear to people working at Input Output Global. That is blockchain diffusion, so the cost of diffusing blocks across the blockchain in real time. And finally, I'll conclude. So let's go into motivation. Why am I working on this design methodology? There are plenty of design methodologies that people have produced over the years. Lots of people know how to build good software, right? You all know how to build good software, I hope. So why do we need a new systems design methodology? Well, let me ask you a question. I always like to start by asking the audience a question. What percentage of software projects fail? Who thinks it's less than 10%? Dear, you have no confidence in yourself, do you? I thought you were all... I was expecting a higher number than 0. Nobody at all? What about 25%? You will in a second. What about 25%? Who thinks 25% or fewer projects fail? 1. 1? Great. 50%. 4, 6, 8, 10, 12, 14, 15, 16, 17, 17 roughly. Sounds about right. 75%? What a lot of pessimists. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22. John, you've worked on Haskell, things don't fail. 90% or more? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Ooh. Here we have the results of the live survey. This is the percentage of software projects that fail according to the audience. And I can see that we have a lot of pessimists in the audience. A majority of people think that 50% or more of software projects fail. In fact, the majority probably is working on 75% or more. And based on my knowledge of statistics, I would say that given that you're a valid sample of the population size, you're probably about right. But according to Wikipedia and research, overall 68% of software projects fail. And interestingly, large projects are more likely to fail than small projects, with 90% of large software projects being failures. Poor requirements analysis incurs a 60% cost premium. Agile techniques don't usually help much, if at all. Sorry, guys, but Agile is not very helpful in making your project succeed. If you fix a problem in development, it costs 100 times the cost of fixing it in design. And overall, there's about $260 billion per year cost for failed projects. So this is a major, major problem. What we want to do is to reduce the cost of software that fails and maximize the percentage of software that succeeds by using good ideas from functional programming. So what are the world's most expensive software failures? Anyone got any idea? How expensive is the world's worst software failure, according to Wikipedia. Any ideas? The null pointer. That's not one software failure. That's a whole family of software failures. Exactly, $1 billion mistake. Well, I'm afraid he doesn't win the prize. The prize, and I'm proud to be British here, goes to the National Health Service for a 12 billion software project, failed software project. So not 1 billion, not 10 billion, but 12 billion pounds, not dollars, okay? Proper British pounds. 12 billion pounds of failure for a cost overrun for an NHC IT project that was originally projected to cost 2.3 billion. So we're pretty good at cost estimation as well in the UK, you'll be pleased to know. This is your tax pounds being spent well by the government. But we're not unique. You can see the US has a very good showing. Sweden has good showing, John, Mary. But amongst the top 20, there are also valiant efforts by New Zealand, by Denmark, by Canada, and by Australia. So there is no uniqueness to failed software projects. I think it's more to do with how hard people try sometimes. Here's some quotes about failures. I'll just read a bit of them out. One of the worst and most expensive contracting fiascos ever. No significant capabilities ready on time. Would have cost $1.1 billion more to just get to 1/4 of the original scope. That's a pretty bad indictment. Project, after completion, was never used, and the agency still today does not have a working IT project. I don't know if it's relevant or not, but if you read this final column here, final two columns, what you discover is a lot of these projects have been outsourced. So there's an idea that outsourcing software avoids cost overruns and improves success. The table here is talking at large projects would seem to contradict that. But it might be that when you're dealing with a large project, you just don't have the capability to do these things in-house, or you don't have to report on them, perhaps, if they do fail. But public data, public source. So what are some key problems with modern software development methodologies? Firstly, they emphasize rapid and flexible software construction rather than careful design. And we've seen that design is incredibly important to managing cost and ensuring project success. Secondly, they fail to adequately consider the essential quality requirements as part of the design. Thirdly, and this is quite interesting and quite an indictment, they fail to consider often whether a system can actually meet its intended outcomes. Will it do what it's supposed to do? You would think it's a pretty basic question to ask, but a lot of people don't ask it. Can it work? And by answering that question, you can avoid a lot of design failure. And finally, failure to consider deployment at scale, trying things out on a small scale, not thinking what happens when you try to scale things up. Okay. And I imagine a lot of these resonate with the experienced developers in this audience. So what we need is good design exploration and system diagnosis. We don't waste time building unworkable systems. Figure out, is a complex system feasible? Will it perform as intended? How can the design be refined so that it always meets its intended outcomes? What happens if you have new requirements? How do your new requirements impact the system design? And that's a big problem. You're all aware that people often aren't aware of the final system requirements when they start a project. Often things change. What then happens very frequently is design decisions are baked into the design, particularly with some software development tools and technologies. It's incredibly hard to change the software. It's not like Haskell, it's not like Scala, it's not flexible. You can't plug and replace things. So you're stuck with software that simply can never work. And then the correct thing to do is to go back, redesign the system, or alternatively, and this is something that people should consider, go back and say, Do you really think those system requirements are the right ones? Because, guys, you're never going to be able to satisfy them. There is no system on the planet, no matter how much money you spend, that can ever achieve what you're trying to do. Okay? Fundamental questions that people ought to answer every time they build a piece of software. Or, finally, why is the system not working as expected? And of course, the answer is functional programming. You're here for Lambda days, it's because you know that functional programming is great. Well, how can functional programming approaches help with software design? They can help us by providing compositionality, they can help by providing structure, and they can help by providing reasonability, which is a term I just made up. We can reason about what the code is supposed to do, about what the system is supposed to do, in a rational way, based on the structure, based on the composition of the design components. And this is one of the points in the paper that Michal mentioned, John's paper from, when was it, 1986, John? It was a long time ago, anyway. Long time ago, from a long time ago. Good, there's a suitable reference. Why functional programming matters, compositionality matters, structure matters, ability to reason about programs matter. These are all part of the key design ethos for functional programming languages. And collectively, these are important because they allow us to isolate different concerns, to consider them in separation, and then to combine the issues to build a complex systems design. So we demand rigidly defined areas of doubt and uncertainty. If we know where the doubt and uncertainty is, then we can build a system that overall can work, and where the doubt and uncertainty is clearly identified and isolated to particular parts of the system. And that gives us a chance to build a complex, distributed, or other system that's actually going to achieve the intended outcomes. And that design methodology, the motivation, is what drives the ΔQ system design paradigm. It's an industrial strength paradigm for system design exploration that allows early prediction of performance and feasibility for complex distributed systems. Now, it's been developed over 30 years by Predictable Network Solutions Limited, PNSOL, and by others. It's been widely used and validated in large industrial and other projects. My colleagues get very nervous when I start to ask them, well, who? Because a lot of their customers actually don't want you to know that they've been using this. But if you look at successful systems, you can probably say, particularly in the telecoms space, well, PNSOL has had a hand in that. And I'll give you some hints about some of those in a second. But they've also helped the government in various ways. They call themselves, colloquially, the wrecker of dreams. They're the ones that come along and say, oh, look, you've spent $1 billion on your project. Never mind the null pointer bug. This thing is never going to work. Your projected spend was $10 billion. By the end of the project, you won't have got anything worthwhile. Save the $9 billion, put it in something else. Okay? Careers are wrecked based on this. Projects are wrecked based on this. I don't think they've wrecked a national economy yet based on this. But things where people are building false dreams, where the dreams do not stand up to reality, bring them in, they help. This technique helps. We've documented this in a paper we produced last year called Mind Your Outcomes, Computers 2022, volume 11, number 45. It's available for free download. There's a lot of detail about what I'm going to talk about in this talk. So what I'm going to do in the talk is to give you some very, very hand-wavy, high-level description without going to any of the details. And I'm happy to go into some of the details with people who are interested, but in particular, one of the things that I won't be touching on in this particular talk is that there is a strong formal semantics that we're developing for these systems. So this is not just a case of you've got a methodology and it's a set of rules and these things seem to work. There's actually a calculus with a formal semantics that allows you to build up things bottom up in a rigid and formally defined way. So what are the properties of ΔQSD, ΔQ system design methodology? Well, it's compositional. It has the concepts of first-class latency and failure. So we're focusing primarily on performance properties rather than functional properties. This already brings the design methodology into an unusual space because people typically don't even think about performance when they're designing the system. But a system that doesn't perform well enough in many areas is simply unusable. Don't leave it to the last minute to think about your performance. It takes a stochastic approach to capture uncertainty in the design, so using various probabilistic statistical methods. Allows performance and feasibility to be predicted at a high system load, even for a partially defined system. So that's very important. You don't need to have the whole system there before you can start to answer questions about the overall performance. The more constructed it is, the better able you are to answer the questions, of course. But an important thing, if you're doing system design and exploration, is to be able to answer the question, is this going to work, before you've actually built the darned thing. Because by the time you've built the darn thing, you've spent the £12 billion, and it doesn't work. You've got a problem. We also add dependencies and multiple timescales to the compositional approach. I'm not going to talk about those in the talk that I'm giving today, but these are a fundamental part of the approach. So, two key concepts. First concept, quality attenuation. So quality attenuation, delta Q, hence the name of the methodology, is first-class latency and failure. A delta Q is a cumulative distribution function. Hopefully everybody has enough mathematics to know what I'm talking about, but essentially what you're doing is what's shown at the bottom of the diagram here. You're building up a graph of the probability of particular delays happening up to 100%. Okay, so you're building up a cumulative distribution function that tells you by this point, with this delay, the probability of this happening is X% until you reach 100%. Okay? Now, there's always a little delta at the end. I've labeled that as F. And the little delta at the end is the probability that your system can never meet the requirements. Okay? Let that sink in for a bit. What is the probability that your system will fail, hence F? So we're quantifying failure as well as success in this methodology. Since you're combining both latency and failure, you can then do things like examine the latency versus failure trade-off. So if you have a stronger requirement for success, then you may have tighter requirements on the latency. If you have stronger requirements on the latency, you may then say, well, your probability of success is lower. So it allows you just to explore this in a consistent way. And then the second key concept is something called an outcome diagram, where an outcome diagram is the system observed from outside. So an outcome is any well-defined system behavior with observable start and end events. Each of these outcomes has its own delta Q, and then a diagram is a causal-directed graph that defines the relationship between all the system outcomes that are required to construct the system, and you calculate the delta Q for the system as a whole. Okay? So in that last sentence or phrase, I've just captured something like 10 or 20 PhD theses. Okay? But that's what we're trying to do. Put things together compositionally from these outcomes, combine the results to create an overall outcome diagram with an overall delta Q that's built up systematically from the individual ones. And you can use this outcome diagram during the whole design process. You can express partially defined systems that are refined from an initial unknown design all the way up to the final system design. Little example down on the bottom right here, what we're seeing are two outcomes, O1, O2, and what you can see is you start with input U1, the result of that is output Q1, final result is output R1, and then what you'll have are delta Q1, delta Q2, which then need to be combined somehow to give you the final delta Q. Details of how you do the combination are in the paper I mentioned. Here's an example to show you how things work. So you've got a single delta Q up on the top left, some input M in, output M out with the delta Q. You've got probability, you've got a delta Q distribution defined from that, which tells you about the quality attenuation. You get a system block diagram, then combining two things, a C1 and a C2, that gives you the outcome diagram. And the D comes from the delta Q. So you can read that off the delta Q, depending on how you're using the system, the design. So how does this work? Well, combine the delta Q from the components to get the overall delta Q for the system. Great, this is functional programming, right? You start with little components, you glue them together. Each of the components does its own stuff. You put them together in well-defined ways, you get well-defined results. Genius, magic. If only we'd known this 30 years ago, John. But then, importantly, if there's something wrong with the delta Q for the system, then what we have to do is to reason backwards to pinpoint the problem. So this methodology not only allows us to build things up and then say, okay, well, we've built it, now what? It also allows us to say, well, actually, look, you've built it, and the way you've built it, that's going to fail. So what you now need to do is to unpick the design, go through the details, and now you can work out exactly why is it going to fail. So which of the components is causing it to fail? And that is where you have to focus on to fix the problem. Or alternatively, you figure out, well, that delta Q needs to be reversed, needs to be reduced further. And ultimately, if you're unfortunate, you get to the point where you discover that one of these delta Qs is simply physically unsatisfiable by the laws of the universe. Okay? And it's an interesting conversation that you then might have with a manager where you say, by the way, you're trying to make light go a little too fast. What you need to do is tell it to back off. And no amount of money, no amount of effort, no amount of shouting at light is actually going to make it run any faster. It goes at its own fixed speed, and we just have to live with it, guys. So one of the interesting techniques that the PNSOL team have developed is the ability of going to very senior people with very bad news and telling them. But a lot of people appreciate that. They realize they're being helped because now they can try something different, right? You were trying to do that. That definitely isn't going to work. Let's go back. And you can use this in two ways. Now, you can use it in diagnosis. You called in, this system is not working. You've got a design you've spent 5 years building. It's not working. Why isn't it working? Or you can use it in design and start from the outset and use the delta Q system design methodology, build up the system, check at each step you're doing the right thing, build the system as a whole. It will always function as intended. It's much better to do the latter. It's better to prevent a problem rather than to try to cure it, of course. And it's also much, much cheaper. So we strongly recommend doing the work on the design at the outset. If you can save a day's design exploration work by spending 5 years working on an implementation if you like. But if you look at the cost analysis, even at expensive consultant rates, we strongly recommend the 1 day work on the system design. Here's a case study, diagnosis. A successful case study, by the way. So what happened was in the UK, the iPhone, the original iPhone, was initially supported by one mobile network operator, MNO. And of course, people didn't like this. They wanted to enter the market. So second one prepared to enter the market. But before the launch, the performance was known to be particularly bad for that new mobile network operator. We're keeping them anonymous, but you can probably guess if you know the UK market. And the first one, because they knew this from inside information, basically gleefully prepared a public ad campaign to run on TV, billboards, etc., saying how bad the performance was going to be for the second one. Okay, so basically exploiting their market position. All good business tactics. Now, unfortunately for MNO number one, PNSOL diagnosed and corrected the problem just before launch, quote, thus saving the bacon of MNO number two. That's a British colloquialism. It means that they pulled the network operator's problem out of the fire. They made it work and saved face as well as making them success. And the result was a 100% improvement in the download KPI, the key performance indicators, which put the second operator now into first place and caused great embarrassment to the first one. So be careful about what you crow about when you're preparing your ad campaigns, and hope that the opposition isn't using the techniques that we're describing, because it can be incredibly embarrassing. Here's the approach that was used to diagnose the problem. Observation points placed at the radio network controller and around the network edges. And then ΔQSD used for diagnosis, determined the outcome diagram for the end-to-end delivery of the packets, measured the delta Q for the intermediate points, isolated the causes and effects to pinpoint the problems, identifying where loss and delay were introduced in an unexpected pattern. So patterns, very important. And ultimately found a solution. Here's a summary of some of the findings that they made. There's more described in the paper. One of the key problems is to do with TCP download throughput, and this was caused by upstream problems from the RNC to the internet, and it was due to particular equipment interactions. So if you looked at the theoretical performance of the equipment, you said, yeah, this is all going to work perfectly. You look at the raw performance stats. But in practice, the equipment interacts in a bad way, and the overall performance is poor. The result they got was to increase the effective TCP throughput by 47%, and this took the MNO to equal first in the market list. And the second key problem was unnecessary fragmentation of user data, which worsened the round-trip latencies, increased transmission load unnecessarily, and caused occasional outages. And by fixing this, by fixing the fragmentation, the unnecessary fragmentation, you got an additional 100% improvement in the HTTP throughput. So that's pretty impressive, 150% or better performance. And that put the second one well ahead of the competition. So that's an example of diagnosis, dealing with a complex system design and delivering, well, I don't know how much benefit to the MNO, but you can estimate it to be in the millions, tens of millions, hundreds of millions, or ultimately in terms of market position, perhaps invaluable. Great. So case study number one. Case study number two, one that I've been working on with my colleagues very closely. So what I just described, diagnosis, something in the past. Design, something we have done and are continuing to do within IO Global, exploiting this ΔQ methodology to deal with the diffusion of blocks throughout the Cardano blockchain. It's an example of how you do system design. So what are we trying to do? Well, the blockchain supports the ADA cryptocurrency, one of the top 10 cryptocurrencies worldwide. One of the most important things we have to do is to deal with block diffusion, allowing an authorized node to create a block and add it to the most recently created block. So basically create the chain itself in a timely fashion. In Cardano, there are important security properties that come from dealing with timeliness within the block production. If you don't produce blocks sufficiently quickly, there's a possibility that you might not end up with a properly constructed blockchain. And that's because the Cardano blockchain, unlike systems like Bitcoin, which are using the energy of Switzerland, uses about 1/10,000th of the energy using a technique known as proof of stake. So it's a much cheaper technique. But to do this, you need to impose certain constraints on the underlying protocol, the consensus protocol, that governs how the blocks are added to the chain. So this is a very important key security property. If you don't meet the security property, you can't guarantee that the chain is correct. Okay? So performance means correctness. The first implementation was done using Rust, and that had insufficient performance. Okay? So the solution was to rebuild the system in Haskell, because obviously Haskell is much higher performance, has much higher performance than Rust. Actually, of course, the technique was to use ΔQSD, focus the design down on the parts that were important, in this case, to do with the network properties, and then to build and define a better networking stack and associated algorithms that could properly support the consensus within the required time. Okay, so I wouldn't want to knock Rust, it's a great language, as is Haskell. So the main design requirement was to achieve 5-second block diffusion time for 95% of the network. And this has to be done in a worldwide setting with a dynamically changing network over public TCP IP and over a network that is unreliable. Okay, so I'll let that sink in for you. You want 5 seconds guaranteed 95% of the time across a common public network. Okay, if you don't do that, your security property is shot, guys. Your system isn't going to work. Okay. How many people experienced a network outage in the last few days? Say the last week. Okay. Yeah, about 50% of us. And how many seconds was that? Was that more than 5 seconds? Yes. This is a bit of a tough problem. If you want to relax some of the properties here, so if you want to say, as some of Cardano's competitors are, and I won't name them, but not people in the audience, I'm sure. If you want to relax some of these constraints, and you want to say, for example, well, let's not go for public TCP IP, let's go for a dedicated network, let's not go for worldwide distribution, because that's too complex. Let's just make sure everybody runs in the same data center using equipment supplied by Amazon or someone else. Then you can reduce the latency and therefore improve the timeliness. And if you assume perfect reliability in a static network, yeah, then you can solve these problems. Okay. Unfortunately, you then create certain other problems like single point of failure. But that's the trade. The reason that Cardano has settled on these principles is because the team is trying to build something which is globally distributed, which is reliable, that can overall, and that can be operated by people with normal internet connections. So nothing particularly specialized is needed to run Cardano. Here is what the block diffusion problem is overall. We've got a series of connected nodes in a graph. So A, B, C, these are all nodes in the graph that are passing on blocks in some sequence. And what we want to know is, if you're going from A to Z, what is the overall block diffusion cost? So what we need to do is to determine the delta Q between A and Z for randomly chosen nodes, 2 randomly chosen nodes, and determine a design so that the delta Q overall satisfies the performance constraints, where the good thing is you can measure the delta Q between 2 points. So you can actually look at 2 points in the system and say, well, what's the delta Q between point B and C, for example, and then use this compositionally to drive the overall design. Several parameters in the design, just listed a few of these. These include things like how frequently do you produce blocks. So Cardano produces blocks overall every 20 seconds. It's actually producing blocks every second and selecting only 1/20th of them. So if you think you've got 20 seconds to produce a block, actually you can't do that because, again, for security reasons, you only want to select a randomly chosen fraction of the total blocks that are being produced. 1 second, yeah, it's a bit of a problem. You've got to do this on real machines, connected to the real internet. You've got to produce a block and get it out, and then take that into account when you're distributing the block throughout the worldwide internet. Yeah, bit of a problem, but doable. Doable. So first step in the process is to measure the underlying delta Qs, the Bs to Cs, so you can build up the overall delta Q graph. And 4 main factors are the block size, the network speed, which is measured from TCP/IP, actual real-world figures, the geographical distance you're covering, because, as I said earlier on, the speed of light is not amenable to manipulation. You have to live with that regardless. And issues like network congestion, which was initially ignored in the analysis, but which we are now considering. So you do that, and what you end up with is a graph that looks something like this. This is in the paper. It's not a trade secret. You can go and download the paper and see the graph. But essentially what it tells you is what we've done is to analyze the delta. We've measured the delta Q for various different sizes of block and various different paths, assuming 2,500 nodes connected in a graph of degree 10. So you have to have something which is some sort of simulation setting. 2,500 nodes is, we think, more than will practically take part in a network, and 10 hops is more than we expect to be necessary in a worldwide connected network of Cardano nodes. So what you can see is, based on that, just looking at the raw numbers, then some of these outcomes are definitely possible. If you look at the 64K mark, then you'll see that 95% of blocks can be produced, in theory, within 1.5 to 2 seconds, for example. So we can use this to guide the design and to tell us when a design is definitely infeasible. And if you look at the top right, what we'll see is 2 megabytes block sizes, if we're trying to diffuse those across the network, are definitely hitting the theoretical limits. Okay, so you can get some idea about what you can practically do, what are the practical limits for the block size, given the assumptions about the network as a whole. The block size we're currently using for Cardano, for reference, is 88 kilobytes. So we know we're well within the theoretical safe limit, and we also know from measurement that we're well within the practical safe limit as well. So step 1, do the measurement. Step 2, do the design. And what we do is to start off with the initial 1-hop design, build that up into multi-hop design, split out the header and the body, so 2 parts to the 2 parts to each transaction, rejoin the network, do the neighbor selection. And in each step, what we do is we have to refine, compute a new outcome diagram, compute the delta Q, and then when we refine it, you either keep the design or decide, actually, this isn't the right design, we'll go back to something we had before. Here's a diagram that shows how a network of 3 blocks can be constructed. So I'm just showing you 3 blocks as an example of a delta Q. Each of the blue shapes is a block that's being produced. Within that, we have a choice between alternatives, so whichever one computes first we can use. And then what we need to do is to combine them across to give the outcome as a whole using the for all quantifier. So you're saying that pick one block, existential quantification, and from each of those choices, combine them together to give a sequence of 3 blocks, and then combine the outcomes. Each of those red points is an outcome diagram. Each of the dots represents a point, a composition point, and then what we do is we build up from this an algebra that allows us to calculate the overall delta Q. So this is just 3 blocks. In a real system, you would have many more. You need to consider the overall system. So final result, worldwide block diffusion over TCP/IP. The design ensures 95% of blocks are diffused within 5 seconds, and we've got a real-time distributed complex system that's been written in Haskell. Pretty good achievement. Don't trust me. These are some numbers that I obtained from our system monitoring this morning. So I've just downloaded these. This is not quite real-time information. It's about an hour old or thereabouts. But this is the percentage of blocks that have arrived within 5 seconds across the network for Cardano. And this shows you the block diffusion. So this shows you the block propagation times over the last 6 hours, where the line is being drawn at 4 seconds. The horizontal line is being drawn at 4 seconds, not 5 seconds. So not only are we not exceeding the requirement, not only are we not hitting the problem area, we're doing much, much better than we need to. There's a bit of capacity there, which is good because the chain is not fully loaded at this point in time. So there's more capacity built into the system. But we're doing live monitoring to feedback to ensure that these real-time constraints are actually being met. Okay, so to conclude. So ΔQSD, design exploration methodology using functional programming concepts, particularly including compositionality and reasoning. It works with partially specified designs, both top-down and bottom-up approaches, and at any point we can check whether the system is feasible, and then eliminate infeasible approaches. We can estimate and predict latency and throughput under high load, which then saves money compared with building the thing and then testing it. So we definitely don't recommend build your system and then figure out if it's going to work. That's not a good way to build an effective system. It cleanly factors the design using these techniques into 3 parts. Compositional system made of independent components, dependencies added between those components, and then we can add multi-level risk management to calculate what is the risk of this particular issue causing problems through the system design, described in the paper that I mentioned to you. What are the next steps? Step 1, collaboration with people in this room and elsewhere to build and improve the tooling to help make the methodology more accessible generally. So we're looking for you to help us on the Haskell tooling and on the front-end design. If you're interested, just come and talk to me after the talk. We've got an ongoing project to formalize ΔQSD. We've got a formal semantics that explains how these rules are constructed, how to build the algebra. That's ongoing work. We're also looking for collaboration to refine the methodology, individuals, companies, and we're also looking, of course, for people to deploy the methodology and to demonstrate that it works in other settings. So to take what we've done here, take it out. It's a living methodology and technique. And there's much more than I've shown you. So there's a practical measurement and computation of delta Q, there's practical experience with large systems, there's tooling, timescales, etc. So if that was interesting to you, please come and talk to me. We're hiring people at all levels, from developers all the way to CTOs for some projects. Come and talk to me in the break after this. Do you have any questions?
Okay, I'm afraid we have only time for 1 or 2 questions, but let's start.
Forgive a bit of ignorance on my end on this, but when I was listening to this talk, it kind of reminded me of like FDR and like TLA plus. So the question I have to ask then is like, is there tooling for like model checking these specs, or or is this like a formal semantic, or am I misunderstanding completely?
Yeah, so you're asking about, are we using model checking tooling?
Okay.
So it's not specifically model checking. Obviously, model checking is related to what we're describing. What we're doing is algebraic. Okay, so so you could say there's a relationship between what ΔQ produces and a model. You could take these components and you could derive a model from those, and you could then put them through a model checking system. Yes, absolutely, you can do that. But what we have is an algebraic system that will calculate and compute the ΔQs for you for a system as a whole. I haven't got a live demo of that, unfortunately, but I hope to show it at some point.
So this design methodology is language independent, and you mentioned that the first implementation was done in Rust.
Yes.
So my question is, why wasn't this design methodology used with the Rust? What is like the advantage of Haskell for implementing this system with its requirements?
Okay, so yes, I meant to emphasize. So great point for the audience here. You can use functional programming techniques, functional programming technology, without having necessarily to use functional programming directly. The techniques apply in any programming language for any system. Obviously, the telecommunications, the iPhone launch people, they didn't use Haskell to do that, unfortunately. We think Haskell is a great language to use, and we used it for our own implementation of the tooling. So the question, why Rust as well? Why Rust first? Well, it's mainly historical, and the short answer is that two projects were started, and the idea with the Rust implementation was they thought they could get a quick and effective working solution sooner than the Haskell solution. Why was Haskell better? Well, Haskell was better because it was easier to, A, reason about the performance characteristics using the techniques we've been using at IOG, and B, to compose and to change the basic software components. Okay, so as I was saying to you, once you've gone down a particular design path in many programming languages, you're stuck with that. Okay, I'm ripping it out, I'm redesigning, that means a major redesign to the whole system. It's not easy to do that in many programming languages.
Okay, let's give a warm round of applause to Kevin.